Hi everyone and welcome to the blood flow and cardiac output section. This is a topic that's pretty interesting to me since I hope to have a career in healthcare. So my goal here is to hopefully not mess this up too much. So one of the first things to realize is that blood flow is an aspect of healthcare that we, basically as patients or just anyone, don't typically try to understand or even wish to comprehend this past the numbers. As you can see from this this pretty heavy chart here on the left, there's a lot going on and there's a lot of different paths and whatnot to follow. So um, let's be honest, if you don't get paid for it, there's not really much of a reason to try to understand. So typically, a physician will ask you to get some tests done, and then you pay for them, and then hopefully you get good results back. Luckily for everybody, though, there's a computer system that typically calculates blood flow via a program. So the physicians, they don't need a full-time mathematician to help them um, figuring out the blood flow, since it's basically sort of an integral, which is why we're learning about this today. So they don't need a full-time mathematician to help them with it, and also one person that would remind them to make fun of them for not remembering their integrals from their undergrad. So let's say you go to the physician, like I said, you ask for this test done, and then they'll get back to you, say, hey, these look normal, they're within the metrics of the expected range, or this is the worst case scenario, they'll say something is wrong and you need some more tests. So blood flow in the arteries or veins is typically measured via a transducer. As you can see here on the right, they typically, oops, sorry, that's my computer making noises, which sends out high frequency ultrasonic sound waves. The reflected waves are picked up and sent to the amplifier so that we are able to hear the waves, and then we can actually discuss them and measure them and whatnot. So physicians are typically looking for decreased blood flow because they're trying to prevent swelling, pain in the legs, weakness, pale skin, and a number of other symptoms like tingling and even blue skin. So since arteries bring oxygen and nutrients to the cell and veins take the deoxygenated blood from the cell and waste like CEO, it's important to maintain adequate blood flow because if you do not, then it can be pretty dangerous for you. So next time you see your parents or your grandparents and they start talking about their swollen legs, discolored skin or whatever, you can bring the possibility to get tested for low blood flow by their physician, and hopefully it's nothing, but if there is something, you can potentially prevent them from getting something worse and get early treatment, which is pretty good. So anyways, this was my section on why monitoring blood flow is crucial and combining it with our extended knowledge of the outside of class. So now let's get to the more difficult part, which is the calculus aspect of this. So as you can see here, this is called Poiseuille's law. This is the French way of saying it. It is also called the laminar flow equation. So let me get this straight. I want to give you guys the good equation. So the equation goes as this. Oops, I'm going to use a pencil. V of r equals capital P over 4 fancy N L R capital R squared minus little r squared. So V of r stands for the velocity. Big R stands for the radius. I have these out of order, but L is for the length, and little r is for the distance from the center axis. Fancy N, I think it's not mu, but it's something along those lines. It's for the viscosity, and P stands for pressure. Sorry if my handwriting is bad. I'm trying to do as best I can. So, since this is our equation to start with, this is Poiseuille's law, Um, in order to calculate this, we have to assume, like I said right here, that the shape of the blood vessel is circular. I mean, it is typically circular, but if you think about it, just for the purpose of this class, we have to assume that it is. Um, so we also, well, as I say down here, just like in a Riemann sum, the circular cross sections that we're discussing are of the same size, making the area right here 2 pi Ri delta R, and you can see out here that delta R is the radius of the outside, so the outer radius Ri minus the radius of the inside, which is basically what we did a couple weeks ago when we used the washer method to find the area between two curves and like different things that we had to do. Since delta R is becoming increasingly smaller, remember delta R is right here, Ri minus 1, it's becoming increasingly smaller. The velocity is almost constant. So this equation can be changed to this one right here, where we keep our area. Whoop, man, it keeps doing this. Where we keep our area right here, our velocity right here, velocity, area, and our delta R that we had discussed. Now we can use a Riemann sum to calculate the volume, the approximate volume of blood across a specific section. So unfortunately, some of us thought that Riemann sums would never appear again, but they keep coming back, as we saw earlier in the semester, and here. So here is the Riemann sum, 2 pi Ri V Ri also, delta R, I equals 1. Oops, that should not be there. I equals 1. And n segments. As section 3.8 mentions, and if you go back in the book, you can choose to do so, or I mean, I'm going to repeat it here anyways. The velocity increases towards the middle of the vessel and decreases towards the outskirts, as can be seen here in this laminar flow diagram. This is due to the friction given by the sides of the blood vessel. So just like using a Riemann sum, the more, and techniques from the numerical integration that we did learn for exam number 2, the more segments you have to break your figure in, or the more precise your answer will be. So the pattern is the same here. And as you can see, there is an n value up here. So the goal is to break this into as many single parts as imaginable. So since the goal is to break this as many portions as imaginable, typically we take the limit to n equals infinity. So yes, the limits are back also, unfortunately, but they are not that bad as we saw in the past couple weeks. I know I keep repeating. I mean, this is why this is something that's important for this class, is because we keep putting back little portions of each little segment that we've learned and putting this together for these applications. So if we take our summation from earlier, here it is, 2 pi Ri V Ri delta R. And we go into an integral. Actually, what we can do is we can put in integral. Yes. So what we can do is we'll have integral of 2 pi Ri V of Ri delta R. But since we need bounds here, what we typically, well, we start at 0, but then we're missing this bound here. But so once we take this bound, I will move this up a little bit. We can take the limit as r goes to infinity, so that our bound is now r. And there's a 0 down here. This goes to 2 pi Ri V of Ri delta, that looks like an A, delta R. If you remember our original equation that I just paused and copied down here, what you can do is you can replace this VR here with that. So it changes your limit of r goes to infinity of your integral r from 0 to r to pi r, which still is your area function. Changes this p to 4 fancy n over L r squared, capital R squared over r little r squared. So what you can do here is a little bit of work. You can cross out this 2 and this 4. That leaves a 2. So your limit of r goes to infinity, which you can take out. You can take out a pi. You can take out a p. You can take out your 2, your viscosity, your L, which leaves your integral of r to 0 at r times capital R squared minus your little r squared. And don't forget, since it's an integral, you need your dr's. So once you do that, don't forget I already took out that first part. You factor in your r, and then you take your antiderivative of that, or your integral, and then this is what you get. So don't forget, your bounds were capital R and 0. And once you factor those in, this is the answer you get. N, which gives your final equation of pi times your pressure times your big radius to the power of 4 over 8 times your viscosity times your length. So this is your final equation, which gives you the flux, which is proportional to the 4th power of the radius of the blood vessel. One of the things to point out, though, is when you do the limit, please remember to not plug in infinity. I know that was something that I personally did a couple times, and I got my fingers slapped. So please remember, you cannot put in infinity, which is why we need to do the limit of this whole thing. So just remember this. So imagine this. Now you're at the hospital. Your uncle gets rushed to the ER or whatever, and they realize that he has an aortic stenosis, and their computer system is down, and they're looking for someone to figure out this blood flow problem that they have. So now you can say that hopefully with this help, you can figure out what to do. And I hope that you have your iPad with you, because it's a lot of equations to remember at the top of your head.